data cannot be collected from the entire population. So a valid question is the sample representative of the population? And actually, is it desirable to have such a property? In this video, we will investigate several sampling strategies and investigate the implications for the estimation of choice models. By the way, for the sake of simplicity, I will assume that all the variables involved are discrete. This is without loss of generality. If you have continuous variables, you just need to replace sums by integrals and probability mass functions by probability density functions. A research process can be summarized into these 7 steps. First, you need to identify your research questions. 2, you need to identify a list of variables that will help you address this question. 3, you will have to assume causality between these variables. Then you will design a sampling strategy. Based on this, you will collect the data, specify a model and estimate its parameters, and then use it for the analysis. In this video, we will focus on 2 steps of this research process. I will briefly talk about the causality assumptions, and we will talk about sampling strategies. In the models that we are deriving, there are 2 types of variables. On the one hand, we have the explanatory variables that are called exogenous or independent. This is what we have usually denoted by X, and examples that we have used are age, gender, income, prices, and so on. So these variables are not modeled. They are exogenous, meaning that they are given in the population. And actually, these are the variables that we use to do policy analysis. We manipulate them to analyze what-if scenarios. The choice variable is called endogenous. This is the variable that is predicted by the model. It's sometimes called as well the dependent variable. In our framework, we have denoted the choice by I, which is the chosen alternative. And by defining the model based on the theory, we have assumed that there is a causal relationship between X and I. So the model that you have derived, the choice model, predicts the probability that alternative I is chosen conditional to X by assuming that there is a causal effect between X and I. This model has unknown parameters theta that will have to be estimated from data. It is important to realize that causality is different from correlation. Let's take an example. Here is a chart where we plot a list of countries, and the coordinate of each country is characterized by, on the x-axis, by the chocolate consumption per capita. It's a kilo per year per capita. And the number of Nobel laureates per 10 million inhabitants. When you look at this chart, there is an obvious correlation between the 2 variables, the chocolate and the number of Nobel laureates. But it would be very difficult for me to justify a theoretical model that assumes causality between these 2 variables in either direction, by the way. So that's a nice example to show that a correlation between data does not necessarily mean that there is causality between them. In the context of choice model, I assume that there is a causal relationship between the exogenous variables, the x's, and the choice, the endogenous variable. And even when there is causality, we need to take care of the direction of the causality. Here is another example of correlated data. Here you have a data set where each point represents statistic about crimes in a country, I don't remember which one, and the temperature. And what you can see is that there is a correlation between crime and temperature. Because of this correlation, I can write 2 mathematical models that can fit the data. The first one would predict the crime as a function of temperature. And the second one would predict the temperature as a function of crime. So this is where the assumption about causality is important. Although I feel comfortable to defend that there is a reason that the temperature has some implication on the crime level, the other way around would be difficult to justify. If it would be the case, putting people in jail to reduce the crime would have an effect on the temperature, and this would be a solution to global warming. Nobody would believe that. So here we have correlation. We assume causality, but we have to make sure that the orientation of this causality is consistent with the theoretical beliefs. So this direction of causality is important because the causality goes from the exogenous variable to the endogenous variable. Okay, and what we are trying to do now is to identify the nature of these variables, which one is an endogenous variable and which one is an exogenous variable. Actually, the nature of these variables depends also on the application. Let's take as example residential location. If you are doing a house choice study, well, this is what you try to predict. Therefore, this is endogenous. But now if you are interested in predicting the transportation mode choice in a city, well, this becomes an explanatory variable, an exogenous variable. Indeed, depending on where you live, your propensity to take the bus or the train or the car will be different. So the point that I'm making here is that you need to identify very early in the process the causal effects or the causal assumptions so that the nature of each variable is well identified, if it is exogenous or endogenous. And this must be done before you start thinking about the sampling strategy and the data collection. Let's now review some sampling strategies. And I will focus here on what we call stratified sampling. What is the idea of stratified sampling? The motivation is that the population is too big to control a sampling mechanism within the full population. So therefore, the idea is to partition the population into mutually exclusive groups that we will call strata, and then we control the sampling within each stratum. The strata do not necessarily need to be of equal size, and this is what is important, they are defined based on the variable selected to be in the model, the one that we identified before. Once the strata have been defined, then we can perform a random sample within each of them. The simplest possible sampling strategy is called simple random sample. Basically, it means that we assume that the population is one stratum. There is no partitioning. In this case, the probability of an individual to be selected in the sample is the same for everybody, and I will denote it by capital R here. This sampling strategy is extremely convenient from a mathematical point of view. Actually, if you do so, the sample has exactly the same statistical properties as the full population. Most of the time in textbooks, this is what is assumed. The sample is representative of the population. Unfortunately, this is almost impossible to conduct in practice. This is why we will need to investigate other sampling strategies. The second type of sampling strategy that we are considering is called the exogenously stratified sample. In this case, the definition of the strata is based on the exogenous variables. It means now that the probability to be drawn or to be selected to be in the sample is not identical for each member of the population. The value depends on the axis. What is important here is that the probability depends on any variable which is not endogenous. So in particular, it may also vary with variables outside the model. It does not matter. What is important is that it does not vary with the choice. So suppose we are interested in a mode choice to commute to work. In this context, it would make more sense to oversample people who are working. Indeed, if we spend a lot of time interviewing people who are not working, it's likely that we will not get a lot of information from them because they are not commuting to work. And we don't want to do it just for the sake of having a simple random sample with equal probability for everyone. Okay, so by using this strategy, we target the data collection towards categories of the population which will give us the most information. Let's take another example. Baby food choice. Well, it is a fact that most of the food for baby is actually purchased by women, mothers. Therefore, if I need to collect data about baby food choice, it would make sense to oversample women versus men in my sampling strategy. And let's consider another example, the choice of a retirement plan. In this context, I'm less interested by people who have already reached the age of retirement. Indeed, maybe these people can tell me about the choice they made at that time, although they may not remember correctly. But I cannot ask them to perform a choice now because retirement is over already. In this context, it makes sense to undersample old people or retired people. When I introduced the exogenous stratified sampling strategy, I mentioned that the strata can be defined on any variable except the endogenous variable, the choice. And this brings me to the next sampling strategy, the endogenous sampling strategy. Well, as you can guess, this strategy happens when the strata involve the choice. The strata definition involves the choice. In this case, the probability for an individual to be selected in the sample depends both on x and I, on the exogenous variables x and on the endogenous variable I. Let's take some example. Take again the transportation mode choice example. It's actually quite convenient to send interviewers into the buses because we have time during the bus ride to interview people. While in a city center, it's less easy to interview car drivers, I don't know, at a traffic light. So I may design my strategy so that I will have more bus riders because it's more convenient to collect the data, as opposed to car drivers compared to what they are really in the population. So I will have proportionally more bus riders in my sample than I have in the population. Another example is about oversampling of current customers. So suppose that I'm working for a company. Well, usually these people, they have the list of their customers. So they don't necessarily want me to draw randomly from the population. They will give me the list and they will tell me call them. They are happy to help us to, for this interview or for this data collection. If I decide to contact the current customers, the proportion of this person in the sample will be larger than they are in the population. And let's take an example of a product which has a small market share. Let's take Ferrari, for example. Ferrari in the context of the car market. Well, Ferrari is a very small market share. So suppose I want to conduct a survey for Ferrari, and because I'm a mathematician, I would like to apply simple random sampling strategy. Well, I will need a lot of data in order to get a sufficient number of Ferrari owners in my dataset because they have a very little share in the population. So if every single individual has the same probability to be selected, I will need a lot of individuals in my sample to have sufficient Ferrari customers. It will cost a lot of money, and Ferrari will tell me, look, this is ridiculous. I have the list of these people, so call them. And if I do so, of course, the number of people who are owning a Ferrari in my sample will be significantly larger than in the population. There is one special case that I will mention because it will help me to simplify the formulation later on, is that when the probability to be selected in the sample depends only on I and not on X, well, I will call this a pure choice-based sample. But as I said, it's a special case of the endogenous sampling strategy. Okay, in order to make these things less abstract, let's take a concrete example. And again, I will consider a transportation mode choice example. So here we would like to predict the transportation mode that is chosen as a function of travel time, let's say. So therefore, travel time is the exogenous variable and the transportation mode is the endogenous variable. In this picture, I have represented the values or the categories of the exogenous variables as rows here. I'm considering 3 categories: less than 15 minutes, between 15 and 30 minutes, and over 13 minutes. And for the sake of this example, I have 3 alternatives: drive alone, carpooling, and transit. The idea of simple random sampling, as we have seen, is that we consider the population to be one group, and we sample randomly in this category here. That's the idea. Now the next strategy that we have seen, the exogenous stratified sample. In this case, the strata are defined by the exogenous variable, meaning travel time. So it means that we define the strata like this. And now I can oversample in some category as opposed to the others. Okay, so I can apply a different sampling frequency in each strata. The next category is the pure choice-based sampling. Well, in this case, the definition of the strata depends on the choice. So I have a strata for drive alone, carpooling, and transit. And again, as I explained before, it may be easier to collect data for transit, so I will have more data here as opposed to here or here. Finally, we have the endogenously stratified sample, where the strata are defined based on the endogenous variables and exogenous variables. And again, the sampling frequency can be different in each cell, depending on your needs, your budget, your objectives, and so on. The key parameter that characterizes these sampling strategies is the probability that each individual in the population is supposed to be selected in the sample. We denoted this by capital R. So let's see how we calculate this capital R. Let's consider a given individual, and this individual has configuration IX. It means that X is the value of his exogenous variables, and I is the choice that this person is making. And because of the definition of the strata, this person belongs to exactly one stratum that we denote by G. And now we will look at several quantities. So capital N is the size of the population. WG is the proportion of people in the population who belongs to group G. We have also characteristics of the sample. NS is the sample size. And I denote by HG the proportion of people in group G in the sample. And now I can calculate the value of R. So R, which is a function of Ix, this is equal to H of G times the size of the sample divided by WG times the size of the population. In this formula, the quantities at the numerator are decided by the analyst. I decide how many people of each category I put in the sample, and I decide about the sample size. The quantities at the denominator are characteristics of the population. I have no control about it, and somehow I have to calculate them. So what are the implications? So as I said, HG and NS are decided by the analyst. Usually the size of the population is irrelevant because we are interested in shares, market shares, and not in the absolute number. I will denote by capital XG the set of values taken by the exogenous variables in stratum G. So for example, in the example that we covered before, the second group was for travel time between 15 and 30 minutes. So that's what XG would be here, the interval between 15 and 30 minutes for this example. I will denote by P of X the proportion of individuals with configuration X in the population. Remember here I assume that X is discrete, so this is just a proportion, but it's easy to generalize it if X would be continuous. Capital CG is the set of alternatives corresponding to stratum G. In the example that we covered before, we had one strata per alternative, so CG would contain one alternative in this example for each of the G. But of course, we could group them. We could have one group for carpooling and drive alone, and one group for transit. So in the first group, we would have CG would be the two alternatives, and in the second group, it would be one. So what is WG? So WG is the proportion in the population of people in group G. So this is the sum over all possible values of X in group G, the all possible value of I in group G, and of the probability to have I and X. But this probability is equal to, so let's write again the sum here of X, the sum over I. It will be the probability of I given X, and this is the choice model. that depends on theta times the proportion of people with variable x in the population. Okay, so this is the values of a WG, and remember you need this value to calculate the probability for each individual to be in the sample. But the interesting thing is that this quantity depends on theta. And the whole reason why you collect data is to estimate this theta. So we have a chicken and egg problem here. The calculation of WG depends on theta. And theta, we don't know it. Okay, so this is the source of the problem that we will be analyzing in the future videos, is the fact that we have this difficulty to estimate WG. There is a simplification though. If we assume that the group G contains all alternatives, it means that CG equals the full choice set. But in this case, the sum over I over CG of P I x theta is equal to the sum over I over all alternatives of P I given x theta, and this is by definition equal to 1. So this is 1, and it means that WG is equal to the sum over x in the group of P of x. And in this case, WG does not depend on theta anymore. It's independent from theta. But this can only happen if the strata are not defined based on the choice. It means that all groups must contain all alternatives. So the groups, the strata, must be defined only on exogenous variables. So this is what we have called the exogenous sampling strategy. In this video, we have reviewed several stratified sampling strategies where the population is partitioned into groups or strata, and a simple random sampling, purely random sampling, is performed within each stratum. Each strategy is characterized by the nature of the variables that define the probability of each given individual to be selected in the sample. When these variables do not involve the choice, the endogenous variable, we will refer to the strategy as an exogenously stratified sampling strategy. And when it does involve the choice, we call it the endogenously stratified sampling strategy.